A medieval carpenter could join two beams without glue or clamps, and the joint would get tighter with time instead of looser. Modern construction requires both, and the joints still fail. The technique that made this possible, drawboring, works through mechanical advantage so elegant that most contemporary woodworkers have never heard of it. In museums across Europe, 17th-century furniture sits behind glass barriers protected from the public that might damage these priceless artifacts. Joined chests from Massachusetts, Welsh cupboards, English benches, tables that have supported family meals for 400 years. What makes these pieces remarkable isn't just their age, it's that they remain structurally sound despite centuries of use, humidity changes, and the natural movement of wood. When conservators examine these pieces, they find something modern furniture rarely possesses: wooden pegs driven through mortise and tenon joints at slight angles, holes that don't quite line up, evidence of a technique called drawboring. Line up. Evidence of a technique called drawboring. This wasn't decorative. It was engineering that created joints stronger than the wood surrounding them, joints that could be assembled without clamps, that required no glue, that actually tightened as the peg was driven home. The technique dates back at least 7,000 years. Archaeologists discovered it in a Neolithic timber box at the bottom of a German well. Egyptian shipwrights used it to build vessels sealed into pits beside the Giza pyramids around 2500 BC. Chinese architects employed it to construct temples that survived centuries of earthquakes. Medieval European joiners made it the foundation of their craft, passing the knowledge through guild apprenticeships where masters taught not just how to cut the joint, but why the offset mattered, and how to read the feedback as the peg drove through misaligned holes. Then something happened. The Industrial Revolution brought power tools that could cut joints faster than hands. Modern adhesives promised bonds stronger than wood fiber itself. Clamps became cheap and plentiful. The economic pressure to build quickly made slow traditional techniques seem wasteful. By the 20th century, drawboring had largely disappeared from woodworking education, relegated to a historical curiosity that hobbyists might attempt but professionals dismissed as unnecessary. Yet the physics that made drawboring work hasn't changed. The mechanical advantage of offset holes pulling joints tight remains as valid now as it was 7 millennia ago. The question isn't whether drawboring works. Thousands of surviving artifacts prove it does. The question is, what exactly did those ancient craftsmen understand about wood, stress, and mechanical fastening that we've forgotten? To understand drawboring, you must first understand the mortise and tenon joint it enhances. This is the fundamental woodworking joint, a projecting tongue on one piece fitting into a rectangular hole in another. The joint works through friction and mechanical interlock. The shoulders of the tenon seat against the mortised piece, providing resistance to twisting forces. The fit between tenon and mortise walls creates friction that resists pulling apart. But friction and mechanical fit have limitations. Wood moves with humidity. A tight joint cut during winter can develop gaps in summer as wood expands. Glue can fail, especially in the hide glues medieval craftsmen used, which softened with moisture and heat. Clamps aren't always practical. Try clamping a timber frame barn or a chair with legs at odd angles. These limitations demanded a better solution. Drawboring provides that solution through intentional misalignment. The process begins after the mortise and tenon are cut and fitted. The craftsman drills holes through both mortise walls while the joint is assembled, marking the hole location on the tenon face with an awl. Then, and this is the critical step, the tenon is removed, and the hole through it is drilled slightly offset toward the tenon's shoulder. The offset is typically around 1/16 to 1/8 inch, what 17th century English joiner Joseph Moxon described as about the thickness of a shilling. When the joint is reassembled and a tapered wooden peg is driven through these misaligned holes, something remarkable happens. The peg encounters the mortise hole first, passing through cleanly. But when it reaches the tenon hole, offset closer to the shoulder, it must bend or compress the tenon slightly to enter. As the peg is driven deeper, this mechanical interference pulls the tenon forward, drawing it tight against the mortise shoulder. The joint closes with force that no amount of clamping could achieve. The peg itself matters enormously. Medieval craftsmen split straight-grained oak or ash to make pegs, working with the wood's natural fiber direction rather than against it. A split peg is stronger than a sawn one because fibers run continuously along its length without being cut. The peg is shaved to a tapered octagon, slightly oversized for the holes it must pass through. This interference fit creates the mechanical force that draws the joint tight. The taper serves multiple purposes. It allows the peg to start into the hole easily, but creates increasing resistance as it's driven deeper. This progressive tightening gives the craftsman tactile feedback. You can feel when the joint has closed, when the tenon has seated fully, when the peg is doing its job. The octagonal shape, rather than round, provides edges that grip as the peg is driven, preventing rotation that might loosen the joint. The offset hole placement is where craft knowledge becomes critical. Too little offset and the peg won't pull the joint tight. Too much, and you risk splitting the tenon or cracking the mortise walls. The correct offset depends on wood species, grain orientation, moisture content, and the size of the joint. Medieval craftsmen learned this through years of practice, developing an intuition about how much draw each joint could handle. The physics is elegantly simple. The peg acts as a wedge, converting the downward force of hammering into lateral force that pulls the tenon forward. But unlike a wedge that can be driven out, the peg locks in place through friction along its entire length. Once fully seated, the peg resists removal with force far exceeding what drove it in. The joint becomes mechanically locked, not just friction fit, but positively drawn together. Modern woodworking relies heavily on adhesives and mechanical clamps to create tight joints. These methods work well for many applications, but they have fundamental limitations that drawboring overcomes through different mechanisms. Glue creates bonds through adhesion between wood fibers and the glue film. Modern synthetic adhesives can create bonds stronger than wood itself. Pull a glued joint hard enough, and the wood fails before the glue line. But this strength has vulnerabilities. Glue requires intimate contact between surfaces. Any gap, even microscopic, weakens the bond. Glue also requires curing time, during which joints must remain under pressure. Temperature and humidity affect cure rates and final strength. Most critically, glue cannot compensate for wood movement. Wood expands and contracts across the grain with humidity changes, as much as several % in width for some species. Longitudinal movement is minimal, but cross-grain movement can open gaps in glued joints. The joint might hold structurally, but visible gaps appear at shoulders, compromising both strength and appearance. Drawboring addresses these problems through mechanical advantage rather than adhesion. The peg continuously pulls the tenon shoulder against the mortise regardless of wood movement. As the tenon shrinks and expands with humidity, the peg maintains tension. The joint can't open a gap at the shoulder because mechanical force prevents it. This is why centuries-old drawbored furniture shows tight joints even after 400 years of seasonal cycling. The technique also eliminates clamping challenges. Clamps apply pressure from outside the work, requiring careful setup to avoid racking or twisting joints. Complex assemblies might need a dozen clamps positioned precisely, all maintaining pressure simultaneously while glue cures. This becomes impractical for large projects or awkward geometries. Drawboring requires no clamps. The peg itself provides the clamping force, applied exactly where needed, in the ideal direction. The joint can be assembled one connection at a time if necessary. Chairmakers discovered this advantage centuries ago. Try clamping a Windsor chair with legs at compound angles. Drawboring made complex assemblies possible without requiring room-sized clamping setups. The mechanical locking mechanism also provides fail-safe redundancy. If glue fails, and eventually all adhesives degrade, a glued joint comes apart. A drawbored joint remains mechanically locked. The peg must be driven back out to disassemble the connection, a process requiring deliberate effort. This is why medieval furniture can be restored even when original glue has long since failed. The technique's superiority becomes obvious in outdoor applications. Weather exposure guarantees glue failure eventually. Waterproof adhesives help, but nothing survives indefinitely. Drawboard joints need no glue. The mechanical lock functions regardless of moisture. Medieval shipwrights understood this. Phoenician joints, a variation of drawboring used in ancient Mediterranean shipbuilding, locked hull planks together with wooden dowels through offset holes. These joints survived centuries submerged in seawater. Perhaps most valuable is drawboring's self-tightening property. As the peg is driven, you feel the resistance increase when the joint closes. There's no guessing whether clamps are tight enough or if glue will hold. The tactile feedback tells you exactly when the joint has achieved full mechanical lock. This certainty, this ability to feel when the job is complete, represents knowledge that power tools and modern adhesives can't replicate. Drawboring seems simple in principle. Drill offset holes, drive a tapered peg, done. But mastery required understanding subtleties that only emerged through years of practice under expert guidance. Medieval guild systems preserved this knowledge through structured apprenticeships that embedded craft wisdom in successive generations. The first subtlety involves reading the wood. Grain orientation determines how the tenon will respond to the stress of drawboring. Straight grain allows the tenon to compress slightly without splitting. Runout or wavy grain creates weak points where cracks can propagate. A skilled craftsman examined each tenon before drilling, positioning the holes to work with the grain rather than against it. For joints requiring two pegs, common in furniture where table aprons meet legs, hole placement demanded additional care. The holes couldn't align with the same growth ring in the leg's mortise walls. Driving two pegs along the same ring line could split the leg. Craftsmen studied the visible grain pattern on the mortise face, offsetting the holes so they crossed different annual rings. This distributed stress and prevented catastrophic failure. The drilling technique mattered as much as hole placement. Medieval craftsmen used auger bits turned by hand-powered braces, maintaining careful control over direction and depth. A hole drilled askew might exit the mortise wall's face rather than passing cleanly through. Through mortise joints, where the tenon passed completely through the mortised piece, required holes drilled from both faces to meet cleanly in the middle. A test of skill requiring precise layout and steady hands. The peg-making process itself embodied craft knowledge. Splitting stock rather than sawing preserved fiber continuity, but not all wood split cleanly. Craftsmen selected straight-grained sections, reading the wood to find natural cleavage planes. The shaving process, typically done with a wide chisel, removed material efficiently while maintaining the taper's consistency. An experienced craftsman could produce a properly sized, tapered peg in minutes. a speed that came only after making thousands. The taper angle itself varied by application. Pegs for massive timber frame joints needed aggressive tapers to generate sufficient force to draw heavy timbers together. Delicate furniture joints required gentler tapers to avoid splitting thin tenons. There was no formula, no mathematical calculation. Craftsmen developed an eye for the right taper, adjusting based on wood species, joint size, and intended use. Driving the peg required similar judgment. Hit too softly and the joint wouldn't close. Hit too hard and you risked splitting the tenon or collapsing the mortise. Walls. The right force came through feeling the peg's resistance, hearing the tone change as the joint tightened, watching for subtle movement that indicated the tenon drawing forward. This sensory feedback, tactile, auditory, visual, created a complete understanding that could never be written down. The guild structure ensured this knowledge survived. Apprentices spent 7 to 10 years working alongside masters, observing thousands of joints being made. They made mistakes under supervision, learning from failure before those failures could ruin commissioned work. They heard masters explain why certain approaches worked and others didn't, building theoretical understanding alongside practical skill. Most importantly, they internalized the judgment calls, the decisions that couldn't be codified, through repeated observation and practice. Master craftsmen didn't just demonstrate technique, they shared accumulated wisdom about wood behavior, about seasonal timing for best results, about which species worked well for different applications. They passed on tricks for rescuing joints that didn't fit quite right, for dealing with difficult grain, for adapting standard techniques to unusual circumstances. This oral tradition, reinforced through daily practice, created knowledge reservoirs that modern woodworking education rarely achieves. The decline of drawboring tracks closely. With broader changes in woodworking economics and education during the 19th and 20th centuries, several forces converged to make traditional hand techniques obsolete even as they remained technically superior in specific applications. Power tool development fundamentally changed woodworking. Mortising machines appeared in the late 19th century, cutting mortises in seconds that previously required 10 minutes of handwork. Tenoning jigs for table saws made matching tenons just as quickly. These machines demanded glue and clamps. They couldn't replicate drawboring's offset, holes, and tapered pegs. But they were so much faster that economic pressure forced their adoption. The speed advantage was undeniable. A craftsman hand-cutting and drawboring mortise and tenon joints for a table might complete the work in hours. Power tools and glue reduced the same job to minutes. In competitive markets where furniture prices fell steadily, manufacturers had no choice but to mechanize. Drawboring became economically irrational despite its technical advantages. Modern adhesive development paralleled power tool advancement. Hide glue, the traditional adhesive, had significant limitations. It softened with heat and moisture, failed in outdoor applications, and required heating before use. Synthetic glues appearing in the 20th century, urea formaldehyde, resorcinol, PVA, offered waterproof bonds, long open times, and room temperature application. These adhesives seem to eliminate the need for mechanical joinery entirely. The marketing of these new products actively discouraged traditional techniques. Adhesive manufacturers promoted their products as superior to mechanical fastening, modern alternatives to primitive methods. Power tool companies did the same, positioning their machinery as progress rather than trade-offs. The guild system that might have resisted these claims had already collapsed, leaving no institutional voice to argue for preserving traditional knowledge. Educational changes accelerated the shift. Woodworking moved from guild apprenticeships to trade schools and then largely out of formal education entirely. What instruction remained focused on machine operation rather than hand skills? Teaching drawboring would require students to hand-cut accurate mortise and tenon joints first, itself a semester's work. With limited instructional time, schools prioritize techniques relevant to employment in mechanized shops. Building codes and insurance requirements created additional barriers. Furniture rated for commercial use often required documented joint strength through standardized testing. Glued joints could be tested consistently in laboratory settings. Drawbored joints, relying on craftsman skill and wood-specific behavior, produced variable results that didn't fit standardized rating systems. Insurers, lacking familiarity with traditional construction, sometimes rated handmade furniture as higher risk despite superior longevity. Most fundamentally, the relationship between makers and objects changed. Medieval furniture was a multi-generational investment. Families expected chests and tables to serve great-grandchildren. This long-term perspective justified investment in techniques whose benefits appeared across centuries. Modern furniture targets shorter lifespans, often designed for replacement within a generation. The durability advantage of drawboring becomes irrelevant if furniture isn't expected to last 50 years, much less 500. The disappearance of drawboring represents more than losing one joinery technique. It signals the loss of an entire approach to working with wood, an approach that worked with material properties rather than against them, that valued longevity over initial cost, that embedded knowledge in physical practice rather than written specifications. We lost understanding of wood as a living material that moves and changes. Medieval craftsmen designed for movement, creating joints that remained tight despite seasonal expansion and contraction. Modern construction often fights movement, using rigid connections that crack when wood inevitably swells and shrinks. Drawboring accepted wood's nature and worked with it. We lost the intimate knowledge of grain orientation, growth ring patterns, fiber direction, all the visual cues that revealed how a piece of wood would behave under stress. Power tools don't require reading wood. Machines cut regardless of grain, leaving craftsmanship to consist of setup and feed rate rather than material understanding. The ability to look at a tenon and know whether it will split when drawbored, where to place holes to distribute stress, this embodied knowledge vanished when hand skills disappeared. We lost mechanical literacy. Drawboring teaches how forces distribute through joints, how tapers convert direction, how friction creates locking action. These principles apply broadly across engineering disciplines. A craftsman who understood drawboring understood mechanical advantage intuitively, not through mathematics, but through hands-on experience with stress and deformation. This physical understanding of how things work together represents knowledge current educational systems struggle to impart. Most significantly, we lost the expectation that furniture should outlast its makers. Medieval craftsmen built for their grandchildren. They used techniques like drawboring not because they were traditional, but because they created objects that would survive generations of use. That cultural expectation, that things should be built to last, disappeared along with the techniques that made it possible. The medieval carpenter who could join beams without glue or clamps wasn't using magic. Drawboring works through mechanical advantage as valid today as it was 7,000 years ago. The offset holes, the tapered peg, the conversion of driving force into lateral pull, all of this remains perfectly sound engineering. We gained efficiency when we replaced drawboring with glue and clamps. Modern adhesives and power tools build furniture faster and cheaper than hand techniques ever could. These are genuine advantages that make quality furniture accessible to people who couldn't afford handmade pieces. But we lost something too. We lost techniques that created joints stronger than the surrounding wood, that required no glue, that actually tightened over time instead of loosening. We lost the tactile feedback of feeling when a joint closed properly, the mechanical certainty of knowing the connection was locked. We lost the ability to build furniture that would serve not just our grandchildren, but our great-great-grandchildren. Most critically, we lost the understanding that durability emerges from working with material properties rather than overpowering them. Medieval furniture survives centuries because craftsmen designed for wood's natural behavior, its movement, its grain structure, its response to stress. Modern furniture often fails within decades because we treat wood as a dimensionally stable material that can be forced into compliance through adhesives and fasteners. The knowledge isn't irretrievably lost. Small communities of hand-tool woodworkers keep drawboring alive. Heritage restoration specialists use it to repair historic furniture. A few furniture makers build modern pieces with traditional techniques, creating work that will outlast them by centuries. But this knowledge remains marginalized, dismissed as historical, reenactment rather than legitimate approach to construction. Building codes don't recognize drawbored joints. Furniture retailers can't market longevity measured in centuries. Trade schools don't teach techniques that can't be mechanized. The ancient woodworking method. Modern carpenters forgot wasn't inferior to contemporary practice. It was different, optimized for different priorities. When longevity mattered more than speed, when materials were too valuable to waste, when craftsmanship was expected to span generations, drawboring was superior. Those priorities may no longer apply to mass-market furniture production, but for anyone building objects meant to last, meant to improve with age, meant to serve descendants not yet born, the technique remains as relevant as ever. The medieval joiner pulling a mortise tight with a tapered oak peg understood something we've forgotten: that the best connections don't fight wood's nature, they work with it. That mechanical locks outlast, adhesive bonds. That joints can be designed to tighten over time instead of loosening. That furniture built to last centuries requires techniques patient enough to create them. That's the real method we forgot. Not just drawboring, but the entire philosophy behind it. The understanding that time and care invested in proper construction pays dividends across generations. The expectation that furniture should outlast its maker. The recognition that working with material properties produces better results than overpowering them. The technique still works. The physics hasn't changed. What changed was our willingness to invest the time and attention necessary to learn and practice methods that only prove their worth across lifetimes. That's worth remembering, even if we never again split oak pegs or drive them through offset holes in hand-cut mortises.